Hi everyone, welcome. Today we're going to be looking at calculating limits using limit laws. And in order to start off this section, we're going to jump right into it, and we are going to start off by observing these limit laws. And these limit laws are sort of the foundation for derivatives once we get to them. Okay, so we have to know how to work with these limit laws, and we have to know when and how they apply in order for us to be able to proficiently work and understand what a derivative means when we get to it in chapter 2. So again, for now, what we'll do is we'll summarize all of these limit laws. And what I want to start by doing for these limit laws is observe that, start off by saying, suppose that c is a constant and the limit of f of x as x approaches a and limit for g of x as x approaches a exist. So again, we don't need to know what they are, we just need to know that they exist. Then the following happens. Number one, when we take the addition of two functions and we apply a limit, then we can separate the functions so that we can find the limit of each individual function first and then add those results. Number two says the exact same thing, except we do it for subtraction. Number three then says, well, if you can take a constant, and again, we defined that c was a constant on the top of your screen. So if a constant is multiplying a function, and we want to evaluate what is the limit of that product, then what's nice about this is that the constant can factor out, and now you have the constant multiplied by the limit of the function, whatever that evaluates to be. So that's looking really good so far. Number 4 says that if we want to take the limit of a product of two functions, then we could initially do it as the product of the limit. No, that's not right. So then we can do it as the product of each individual's limit for the function. So take the limit as your function f of x approaches a, multiply that quantity by the limit as g of x approaches, limit for g of x as x approaches a, take that product and multiply it by the first. Then number 5 says that if we can divide the two functions f of x divided by g of x and then analyze that limit, well, the same works if we were to evaluate the limit of the numerator, which would be the limit for function f of x as x approaches a, and divide that by the quantity for the limit of g of x as x approaches a. And of course this works provided that the denominator, that limit that gets evaluated for g of x, is not 0. And then we have the properties or these laws from 6 to 9. Number 6 says that if we take the limit of a constant function, then we naturally just get the constant. Number 7 says if we take the limit of the identity function, then the limit is just the numerical value itself. If we take, number 8 says if we take the limit for a polynomial function, or in this case a power, x to the power of n, then when it evaluates it becomes a to the power of n. Nice, that one looks almost like a direct substitution that we can definitely use. And then number 9 says that if we can take the limit as x approaches a for the square root of a function, or not necessarily a square root, for the nth root of a function, then we can take the nth root of the limit of f of x as x approaches a. So again, we have a lot of limit laws here, and we want to make sure that we reference these limit laws. That way we can get accustomed to using them. And what I want to do at this point in time is I want to start using those limit laws here on part A. So looking at part A, I'm going to start implementing these limit laws. Now notice, in part A, I want to find the limit of the product of these functions as x is approaching -1. And what I'm going to do is I'm actually going to use limit law 4 here. So I'm going to use limit law 4, and I'm going to state this here, that I'm going to say limit law 4. So that's the one I'm using here. And that's going to be that I can take the limit of each individual function. So this is limit as x is approaching -1 for x to the 4th minus 3x. That's the first part. Second part says I can take the limit as x is approaching -1 for the function of x squared plus 5x plus 3. Okay, so there we are. We're using limit law 4 there. Now what I can do is I can say, okay, now identifying each individual limit, I can go through and I can then start using the rest of my limit laws. So for the next step, what I'm going to do here is I'm going to use limit law 1, or in this case limit law 2, which says that if I have the subtraction of two functions, then I can take the limit of each individual function and add those results as such. And the same thing is happening to the second factor. And one more, limit as x is approaching -1 for 3. There we are. So again, what I'm applying here is I'm applying limit law 1 and limit law 2. Excuse me. Now, wherever I see fit, I can start evaluating those limits. So the first term is the limit as x is approaching -1 for x to the 4th. This limit law here is provided by limit law 8, that I can do a direct evaluation now because I have a variable to an exponent. So in this particular case, I just insert -1 into that power. And here I say that I was using limit law number 8. Well, for the next limit law, there's a constant multiplying a function. I factor out that constant as such, and now I'm left with this result. Okay, and so here we had a limit law where we were using the constant and we factored out that constant. So for this step, I used limit law number 3. Now, going back to that second set of parentheses, again, this limit as x is approaching -1 for x squared. What I'm going to do here is I'm going to use, once again, limit law number 8 and do a direct substitution here. Therefore, again, I'm using that step number 8, or lot number 8. For the second term, I'm going to use the law where I factor out that constant. Again, that was number 3. And for the last one, I'm actually going to use limit law number 6. Notice that 3 is a constant, so this is the limit of a constant number 3 as x is approaching -1. So by limit law number 6, this tells me that I should wind up with a 3. Oops, I'm sorry. Limit law number 6. There we go. So that's really great now, because now all I need to do is evaluate just two more limits. So the first coefficient, or the first constant here, -1 to the power of 4, it's just 1, minus 3 times this limit, and this is going to be a direct substitution limit now, which is limit number 7. So I evaluate here, and I used property number 7. All right, and then I simplify the first term on the second set of parentheses. That's going to be a 1. I evaluate this limit here, which will just be 5 times -1. Again, what I did is I used limit law 7, and I still have a 3 here. And what I have here now is I have a really nice set of algebra steps that I now need to perform. So this is going to be 1 minus 3 times 7. All right, so that's going to be 20 negative 20. There we are. Looking pretty good. Wow, I just realized I made a mistake. I was wondering why my numbers were coming out so high up. So my mistake is here on this step. I accidentally inserted a negative 7 when the evaluation for this limit is supposed to be negative 1. My apologies there. Okay, so here we are. Now that that step is fixed, so the first parenthesis now gets me 1 minus 3 times negative 1, which will then turn into 1 plus 3, which will be 4. And the second set of parentheses now gets me 1 minus 5. So 1 minus 5 gets us negative 4. Then negative 4 plus 3 gets us negative 1. So our final result is negative 4. Now, one of the items that I'm going to ask you to notice is what would have happened if instead we would have just done a direct substitution from the very beginning. Sorry, I'm letting that helicopter pass by. There we go. Okay, so what would happen? Well, I want you all to investigate that. Do we still get the same result if we were to evaluate the initial polynomial product at x is equal to negative 1? So give that a shot and see if you get the same answer. I think you might be surprised. Or maybe not. Part B. Let's go with the limit as x is approaching negative 3. And this is going to be for x squared plus 3x divided by x squared minus x minus 12. Okay, so we're going to go through once again, and we're going to be performing the same steps. Okay, so the first thing that I see is that I can take a limit as x is approaching negative 3 for my numerator, which is x squared plus 3x, divided by the limit for my denominator, which is x is approaching negative 3, for x squared minus x minus 12. And again, the limit law that I'm using here is limit law number 5. So we haven't used number 5, and here it is. So we use limit law number 5 to get us to this step. Once we get to this step, we can then, as you might have found out, try direct substitution for the numerator and denominator individually. For my numerator, we get negative 3 squared plus 3 times negative 3 divided by negative 3 squared minus the quantity of negative 3 minus 12. We simplify, so that my numerator is 9 minus 9. And I'm just double checking here. Oh, no. Yes. So I have, there we are. Okay, negative 3. Negative 3 squared gets us 9. Okay. Divided by negative 3 squared gets us 9 plus 3 minus 12. And what we get here, well, if we keep going, numerator is 0, denominator is also 0. Uh-oh. Wow, something happened here. Interesting. This here, uh-oh. That's bad for us. This is actually called, it has a very specific name. This is actually indeterminate form. So indeterminate form. Uh-oh, we have an issue. And there's our issue. Is that we found an indeterminate form. What that means for us is that we now need to apply either some algebra work to simplify our initial expression, or we need to do some trigonometry substitutions in order to try to justify this. However, since there are no trig equations mixed in here, I want to stick with the whole algebra concept. So instead, I'm going to bring the work down here, and I'm going to start again, but this time I'm going to start a different way. I'm going to start by factoring. The numerator, I have x, so I pull that out. Denominator is a trinomial, and that trinomial should, or I should say, does factor. Notice what happens here. X plus 3 will simplify in that numerator and in the denominator, which then, coincidentally for us, makes the world of difference, because now we're left with x divided by x minus 4. Try a direct substitution here, and we get negative 3 divided by negative 3 minus 4, which turns out to be negative 3/7. Here's the moral of the story. The moral of the story is that I got this wrong. Wow. Cheese and crackers. It's supposed to be positive. My apologies. It's positive because the numerator and denominator are both negative. So the moral of the story here is, if you can factor and simplify before we start applying these limits, do them. You will see that in doing so, you will find it a whole lot easier to evaluate these limits. And in a way, that's kind of why we drudged through all of those semesters of algebra and trigonometry, was so that algebra, or in this case factoring, could be very beneficial to us, and it could come as second nature. I often tell a lot of my calculus students that your best friend in Calc 1 is factoring at all times. I found that to be true when I was a student, and I still find it to be true as an instructor when I'm looking at different calculus students come into my class. Factoring is one of the best methods all around to simplify certain expressions. Now, what I'm writing on here, I'm writing the direct substitution property. And the direct substitution property is kind of what you just saw previously in part A and part B. This says if your function f is a polynomial or a rational function, and A is in the domain of your function f, then the limit as x is approaching a for f of x is equal to f of a. In other words, we get a direct substitution, kind of like what we analyzed in part A, that we said, hey, we could possibly do this. Now we come to find out, yes, we definitely can do it, and it doesn't just apply for polynomial functions, it also applies for rational functions, so long as A is in the domain of the function. Now, notice in part B, if we initially look at the domain for that function, we get that x cannot be negative 3. But when we simplify, when we factor out the numerator and denominator and simplify, we get that that new function, x divided by x minus 3, x divided by x minus 4, that one can hold the denominator of negative 3 when x is negative 3. Therefore, we kind of bypass it in a way. So we got the direct substitution property, which is super duper nice for us. Now, let's keep looking, because a lot of times we want to make sure we know how to evaluate limits. And some of my favorite limits are limits that involve piecewise defined functions. So here I want to take the limit as x is approaching 1 for my function f of x. And this function is going to be where f of x is equal to the piecewise function for x plus 1, and this is going to be for x is not being equal to 2, and then negative 3 for x being equal to 2. Okay, so we got some work to do here. Excuse me. Now, we're going to start analyzing this. And we're going to say, okay, well, let's start trying to evaluate this limit. Can we do a direct substitution? The answer here is yes, you can do a direct substitution. However, you then have to identify which individual piece are you on for this piecewise defined function. In order to find this, well, we then look at the x value that my limit is approaching. My limit is approaching 1, or limit as x approaches 1. I have no restrictions on this function for 1. Which means, what is my answer? Well, my answer would then come in the form of this first limit. In that instance, I can just say the limit as x is approaching 1 for f of x, this is going to equal my limit as x is approaching 1 where the domain exists, and that's on x plus 1. Because this holds all of your x values when x is not equal to 2. X is 1 for this particular case, therefore we can use that first equation. And therefore when I evaluate, I get 2. Now here's a tricky part. Okay, so here's the tricky part. What if instead of this, I were to ask a different question, and this question would be, find the limit as x is approaching 2 for f of x. Same thing, where we have the same function. What would the answer be then? Interesting. I love these kind of interesting thought questions because the answer is actually not as intuitive as you might think. Or maybe you do, and that's great. This limit as x is approaching 2 is actually 3. Why is it 3? Because we do a direct substitution. Now, how can we view this? You might say, Mr. Castro, how is that possible? You know, we're looking at this and we're looking that that function is a linear function, but it is a piecewise defined function, and you would be correct on that. However, we're not trying to find the x value. We're not trying to find the function evaluated at 2. We're trying to find out what is the limit at 2. And finding the limit and the function evaluation of a function are two different things. Sometimes they're the same concept, and that's fine. Sometimes they're not. And we want to focus on, in this particular case, the time that they're not. All right. So here's why. I'm going to graph that function. I get x plus 1, so that's going to be an intercept at 1 and a slope of negative 1. Here we are. And we're also going to get negative 3, so let me go down to negative 3. There we are. Negative 3, that's going to go down to negative 2. So here we are. Okay, good. So here's my line. and this is my function f of x. Notice when x is equal, oops, my apologies. Geez, I'm way discombobulated on this. It's very late night. It's okay. So when x is 2, we get that my function value is going to be negative 3. So what's happening here is this, that at x is equal to 2, I will go down to negative 3, and here's going to be my function value. That means that my function value up top, up here, does not exist for x is equal to 2. That means we have an open circle there. Now, back to how I was talking about this limit, how I was trying to represent this limit. This limit, well, as x is approaching 2, for this question down here, x was approaching 2, but on the function, as we're traveling along the function to that output is going to just be the self up here, or sorry, that output would just be this output here of 3. And that's where we get this limit. Is that the output wants to be 3. However, it has a removal of discontinuity, which moves that piece of the function downward. And that's what we call it, a removal of discontinuity. So we must be careful when we're looking at these individual functions, especially for piecewise defined functions. They might not always be as straightforward as you see. Sometimes you might use visuals to try to extract what the limit is. And I highly, highly encourage that. So let's evaluate the limit here. Part A. So here's the limit. This one's going to be the limit as u is approaching 2 for the numerator of the square root of 4u plus 1 minus 3, all divided by u minus 2. Now again, you can go with the direct substitution process. However, in this particular case, I want you to notice the denominator. The denominator cannot take in a value of 2. However, we're trying to evaluate as u is approaching 2. So in this particular case, direct substitution doesn't work directly, which means we have to somehow, some way, find a manipulation to make sure that we're able to get it to work. So in order to do this, what I am going to do is I am going to rationalize the numerator. Rationalizing the numerator is one of those techniques that we picked up somewhere along the lines of algebra class. Now again, here, this step is rationalizing the numerator. Now, you can rationalize the numerator or you can rationalize the denominator. The process is always very, very similar. So now, when we do this, we get the limit as u is approaching 2 for the function, and we multiply. We multiply the numerators together here. So multiplying the numerators, notice it's a difference of squares. So when we multiply, we get 4u plus 1 minus 9 divided by, let's see the denominator here, we're going to get u minus 2 multiplied by the square root of 4u plus 1 plus 3. And there's my denominator. Notice I'm not combining my denominator. I'm not multiplying my denominator. It's typical for the process that when you're doing this, you try not to multiply and distribute. Instead, you just want to show that you're multiplying and leave it like this. because oftentimes you will be able to factor and simplify, and in that process, if you already simplified or if you distributed, then you're going to have to undo that to factor in order to try to simplify it. So it might take you a few more steps if you do distribute, and so that's why we want to stay away from that distribution. Now, the numerator here, for the numerator, we have 4u minus 8, all divided by the same denominator, which is u minus 2, multiplied by the quantity of the square root of 4u plus 1, then plus 3. So again, now looking at that numerator, I can factor out that numerator now. So factoring out that numerator, I get the limit as u is approaching 2. The numerator now factors into 2 times, or actually 4. 4 times u minus 2, all divided by u minus 2, multiplied by the square root of 4u plus 1, and then plus 3. And now we can simplify those u minus 2's. In this particular instance, we're now left with limit as u is approaching 2 for the quantity of 4, all divided by the square root of 4u plus 1, and then plus 3. Now, it's at this point in time that the domain is now satisfied, that we can now choose values like 2 to make sure we make that substitution. So if we do a direct substitution here, we're now left with 4 divided by the square root, that's going to be 8 times 2, 4 times 2, which is 8, plus 1, which is 9, and then plus 3. Square root of 9 is 3, so 3 plus 3 is 6. Then we're left with 4, 6, or in other words, 2/3. There's our answer. Nice, neat, and concise. Love that. Let's look at part B. Part B. We want to observe the limit as h is approaching 0 for the quantity of 3 plus h to the power of negative 1 minus 3 to the power of negative 1, all divided by h. And again, we have to try to go through the whole process. Identifying first that if you try a direct substitution, that denominator will then go to 0. Hence, we have an issue. We must try to do some algebraic manipulation here. So in order to do this, what I'm going to use is the property for negative exponents. This property for negative exponents says that I have 1 divided by the quantity of 3 plus h, and that's the first quantity, which was 3 plus h to the power of negative 1. And then I have plus 1 divided by 3. Not plus, my apologies, minus. There we are, so minus 1 over 3. All of this is then going to be divided by h. Now that we have this complex fraction, what I'm going to do here is I'm going to multiply the numerator of this complex fraction and the denominator of this complex fraction by the LCD, which in this case will be 3 times 3 plus h. As such. And so this is complex fraction simplification. Alright, so once we're able to perform this, then we're going to go ahead and distribute that numerator that I was looking at, that I was going to multiply by. This is going to multiply the first term here. And now when it multiplies the first term, then we're going to be left with a numerator of 3. The second term is going to multiply that numerator. Again, we're going to be left with minus 3 plus h. divided by h multiplied by 3 plus h times 3, as such. Okay, so look at that numerator now. That numerator can now simplify just a little bit more. And the way we simplify that numerator, 3 minus 3 just gets us 0, so distribute the h, or the negative. So we get negative h divided by h times 3 plus h times 3. Look at that. The h's now simplify. Very nice. And we're left with the limit as h is approaching 0 for the quantity of negative 1 divided by 3 times 3 plus h. Now we can do a direct substitution. If we make the direct substitution now, we get negative 1 divided by, so negative 1 divided by 3 times 3, so we get negative 1/9. Awesome. I like that. All right, looking pretty good so far. So we got part A and part B down. That's great. Now, one of the items that I want you to pay attention to, because this is one of my biggest pet peeves in Calc, especially Calc 1, when we start learning these limits. I want you to keep the string of equations or the string of equality here. If you're doing this work, show the work that you're doing it embedded in the step that you're going to use it in. And simply because if you're manipulating this expression, I want to see that you're manipulating this expression using the limit argument that we have, which is limit as u is approaching 2. Also, notice that when I actually took the limit from this step that I am highlighting on the screen right now, from this step in red to the step in green, notice the step in red, I arrived and I said, okay, now I'm going to use a limit. And in the next step, the one that I highlighted in green, the one right below that, is where I then applied the limit. And then notice the limit notation is gone. This is why it's important to use proper notation. If you accidentally drop the limit from your work, then it indicates to me, or it indicates to the reader, that you have now applied the limit. So you can't make the limit notation vanish and then reappear again 5 or 6 steps later, because then you're going to leave me or the reader all confused. So you have to make sure that your arguments are well structured and that your work is somewhat organized and that you're using proper limit notation. Okay, so that's what I wanted to say about limit notation. Now, let's look at a different one. Let's look at part C. So here goes part C. For part C, we then want to identify what is the limit as x is approaching 6 for the quantity of 2x plus 12, all divided by the absolute value of x plus 6. All right, that looks interesting. So we're going to keep that in mind. All right, so before I start, or before I begin with this, I actually want to observe the absolute value function. All right, so I'm going to start a bit of scratch work, and I'm going to start that scratch work on this side, on the right-hand side. So what I'm going to do is I'm going to look at my function f of x, which will be the absolute value of x. The absolute value of x is a piecewise defined function. And it's a piecewise defined function because we take on positive x values if the x values are greater than 0. We take on negative x values if the x value is less than 0. Okay, and we're going to hold on to that. Simply because what I want to do at this point in time is I kind of want to evaluate the function that was given to me using this process. So in order to start this process, what I am going to do is I am going to start working with this function in terms of its pieces. And the pieces come from the denominator because that's the absolute value. So what I'm going to do here is I'm going to use f of x, or let's just go with the absolute value of x plus 6. What does the absolute value function tell me then, the one on the right? Well, this says that the argument inside of the absolute value is the argument itself. In other words, it's just x plus 6. And this works if that argument is greater than 0. So this works if the argument is greater than 0. Okay, that looks pretty good so far. Next, the second piece. We then have to consider the negative version of the argument. So that's what I'm going to consider here. The negative version of that argument. So negative the quantity of x plus 6. And we only use this argument here if this argument, if x plus 6 is less than 0. Okay, so let's simplify and let's clean this up. So what we get here, the first piece, x plus 6, works if we have, I'm going to manipulate this boundary or this, let's say, domain restriction to solve for x. So this only works if x is greater than negative 6. Okay, let's work on the bottom function. So for the bottom function, the bottom piece, I'm just going to keep it as negative x plus 6. I'm not going to simplify there. And this only works, I am going to simplify this domain restriction. This only works if x is less than negative 6. Great. That's where I want to be. Now, why is that where I want to be? Well, more specifically, because looking at this function, the one that was given to in part C, check this out. What's going to happen in part C is that I now have the limit as x is approaching 6 for the quantity of the factor of 2 times x plus 6 divided by the absolute value of x plus 6. And I'm going to tell you this right now, please, please, please do not cancel. Please do not simplify the numerator and denominator, as they are not the same. They are not the same because we get two different pieces, as we can see from the piecewise function. If you were to cancel it out, you would only be canceling out one of the pieces, which means the other piece still exists, and that's the one that you are not accounting for if you do cancel. So please be careful with that. Okay, so now I want to analyze this given function here. Okay, so that's a function that I want to work with. All right, so let's look at this just a little bit more. Okay, so what I'm going to do now is I'm going to create another function. All right, so this other function is now going to be the numerator, is now going to have the numerator of x plus 6, and it's now going to have the denominator of the absolute value of x plus 6. And what I'm going to do is I'm actually going to use this as a reference, which is my previous absolute value piecewise defined function, the one that I have right above the one I just wrote. I'm going to use that as my reference. So I take the numerator, because the numerator is arbitrary here, so it's just x plus 6. Divided by, this is where the pieces come in. The denominator, one of the absolute values, says that I just need to keep it positive. So I keep the denominator positive, and this works again, that first piece, if x is greater than negative 6. Well, the second piece is numerator x plus 6. Denominator is the negative version of that, which means it's negative the quantity of x plus 6. And this works if x is less than negative 6. Okay, that's looking good so far. So now all I need to do is simplify them. Well, check this out here. We can simplify this. Look at the first piece. The first piece we get 1 if x is greater than negative 6. And the second piece we get negative 1 if x is less than negative 6. That's interesting. Because now, again, we have a piecewise defined function. And as we start approaching our values here, all right, so as we start approaching the values that we're going to look at, I'm going to make a small change. That small change is going to come over here in part C, where I'm not going to be approaching 6. Instead, I'm going to be approaching negative 6 to make this a little bit more interesting. As we start approaching negative 6, this function takes on two different values. Well, one value it takes on from the left-hand side. The other one, or sorry, from the right-hand side. The other one it takes on from the left-hand side. So we have two different limits. We then, in order to find this overall limit, need to consider the limit as x is approaching negative 6 from the left-hand side for this function for 2 times x plus 6 divided by the absolute value of x plus 6. Well, let's see. If we're approaching negative 6 from the left-hand side, negative 6 from the left-hand side, we're going to evaluate to be negative 1, which means this limit as x is approaching negative 6 is going to multiply 2 times negative 1, which will then get us negative 2. Similarly, we evaluate the limit as x is approaching negative 6 from the right-hand side. And so if we approach it from the right-hand side, oops, that was negative up there, negative 6 from the right-hand side. So as we approach it from the right-hand side, we are now approaching 1. So now we get to see, look at the left-hand limit and look at the right-hand limit. Left and right-hand limit are not the same, which means the overall limit that we're trying to evaluate for does not exist. So the limit as x is approaching negative 6 for 2x plus 12, all divided by the absolute value of x plus 6, does not exist. And again, we went through the whole argument of trying to look at what a piecewise defined function is actually doing. All right, so again, we keep that in mind. Now, if you wanted to see this graphically, we can definitely view this graphically. Okay, for that, I'm going to use my friend Geogebra. So follow me along to Geogebra. All right, so here we are on Geogebra. And what I'm going to do is I'm going to use that quantity of 2x, there we go, 2x plus 12. And again, that's my numerator. And then I'm going to use my denominator. My denominator is going to be the absolute value of x plus 6. There we are. And then I'm going to take my numerator, which in this case is my function f of x. So I'm going to take f of x. So take f of x, and I'm going to divide it. And we're going to divide it by g of x. So divided by g of x. And I'm going to hide the other functions. There we are. Now you can see these are just constant functions. So as we're approaching negative 6, from the left-hand side, we're at negative 1. Sorry, we're at negative 2. As we're approaching negative 6 from the right-hand side, we're at positive 2. And that's exactly the conclusion that we arrived at using the algebraic manipulation. So there are multiple ways to view this. If you want to view it in a graphical sense, by all means, be my guest and make sure you graph it correctly. If you want to do it algebraically, then the work algebraically is done on the whiteboard that we were working on. So that's awesome. Now let's talk about one more item before we wrap up this section. So follow me back.